So let's practice with using Adam optimizer to find the local minima of some function. So the task will not be to find the minima itself, but to try some iterations of this algorithm. So let's go and try it. So let's say we have a function f of x, y, which is equal to x squared plus y squared plus 1.5 xy plus 2x minus 1. We start from point m0 with coordinates -1 and 1, and we want to try Adam optimizer with eta equals to 1, beta 1 equals to 0.9, beta 2 equals to 0.8, and epsilon is 10 to the power of -5. So let's find the first thing, which is the gradient. So we want to find the gradient of function f. It will be our vector 2x plus 1.5 y plus 2, and then 2y plus 1.5 x minus 1. So we will put our first m0 as 0, 0, and our first v0 as 0, 0, because we didn't have any iterations before. Now let's calculate first our first iteration. So we need to calculate g1, which will be our gradient at point m0. So we calculate 2 times -1 plus 1.5 times 1 plus 2, 2 times 1 plus 1.5 times -1 minus 1. So this is -2 plus 2 will be 0, just 1.5, and 2 minus 1, 1, 1 minus 1.5 will be -0.5. So this is our G1. Now it's time to calculate MT and BT, our moment. So this is M1, beta 1 multiplied by M0 plus 1 minus beta 1 multiplied by G1. So beta 1 is 0.9 multiplied by 0 vector, which is M0. Then 1 minus 0.9 will be 0.1 times the gradient. And after all the calculations, we will have 0.15, negative 0.05. Now we can calculate V1. So it is beta 2 times V0 plus 1 minus beta 2 G1 squared. So beta 2, no, we have 0.8 times 0 vector. Then 1 minus beta 2 will be 0.2 times square of the gradient. So our gradient is 1.5. The square will be 2.25. The square of 0.5 will be 0.25. So after multiplication of those values by the 0.2, we'll have 0.45 and 0.05. So we found M1 and V1. Now we move to M hat 1, which will be just M1. So our vector. divided by 1 minus beta 1, which is 0.9, to the power of 1. So it will be just division by 0.1, which will restore our initial gradient, which is nice. So now we can calculate V1 hat. So our value 0.45, 0.05 divided by 1 minus beta 2, which is 0.8, to the first power, which is just 0.2. So it will restore the square of our gradient. Now we can calculate our new x. So x2 will be our new value. So our old value, which is minus 1, 1, minus eta, which is 1, divided by square root. So we'll have the square root of 2.25, 0.25, each added to the epsilon, which is very small value, so we will disregard it. But you can try and see that we can do this. And now it's multiplied by n hat. So I will have minus 1, 1, minus vector. So the square root of 2.25 will be 1.5. 1.5 divided by 1.5, this first component. And the second component will be negative 0.5 divided by 0.5, which is square root of 0.25. So this division all is just 1 and minus 1. So minus 1 will be minus 2. 1 minus plus 1 will be 2. So this is our new values. Let's try to do the second iteration, and it will be our final iteration. Before we do this, let's calculate the function f. So what was the value of f at minus 1, 1? So we can substitute those values and find that the first value was, so here we have 1 plus 1 minus 1.5, 2 minus 1.5 will be 0.5, then minus 2 will be negative 1.5, and minus 1 negative 2.5. So what is the value of f at our x2? So we have minus 2 and 2. We will have minus 2 squared 4 plus 2 squared 4 plus 1.5 times 4 will be 6, and it will be minus because we have minus 2. Then I have minus 4 and minus 2. So 4 cancelled. This will be 8. 4 minus 8 minus 4. So we a lot improved. We had minus 2.5 and we have now negative 4. So we improved our value. Now let's calculate the second gradient. This is the value of the gradient at our point x2. So minus 2 minus 4 plus 3 plus 2. Next will be 2 times 2, 4, minus 3 minus 1. So our value will be minus 4 plus 3 minus 1 plus 2, 1. And 4 minus 3 minus 1 will be just 0. So this is the value of our gradient. Now we can calculate M2 and V2. So M2 is beta 1, which is 0.9, times old value, which was 0.15 and negative 0.05, plus 0.1 times our new vector 1 and 0. So we will multiply 0.9 by value 0.15, and then add 0.1, we'll have 0.235. Now multiplication by 0 will not give us anything new, so we will have negative 0.045. Now we can calculate V2. So this is 0.8 multiplied by the old value, which was 0.45 and 0.05. Now added 0.2 times square of our gradient, which will be the same, because we are lucky with that. So 0.8 times 0.45 plus 0.2 will be 0.56, and 0.8 times 0.05 will be 0.04. Let's now calculate M2 hat and V2 hat. So M2 hat will be our M2, which is this value, 235, negative 0.045, divided by 1 minus 0.81, because now we raise 0.9 to the second degree. So it will be 0.235 divided by 0.19, which is 1.2368. Now we do the same with the rest, which gives us negative 0.2368. So let's now calculate V2 hat, which will be our V2, 0.56, 0.04, divided by 1 minus 0.8 squared will be 0.64. So we divide 0.56 by 0.36. We will get 15556. So I approximate values. 0.4 divided by 0.36. I will have 0.01. Okay, now I can get new x. x3 will be the previous x, minus 2 minus 1 times m hat divided by square root of v hat plus epsilon. So we actually can add epsilon if we want. So let's add epsilon. 55557. And here I will have 11112. So if I expand, because this is the like that, I will have something like that. Okay, now minus 2 minus, so we will have a division 1.2368 divided by this square root. So we calculate the square root will be 1.2472, and this fraction will be minus 0.2368 divided by the square root of that will be 0.3333. So I will have minus 2 minus. Now let's calculate this expression. It will give us 0.99166, and here I have 2 minus 2 minus will be plus, so I will divide 2368 by 3's, and I will get 7105. So the value is negative 2.99166 and 2.7105. So that's how it goes. Now we can calculate the function f at this point x3. So I will use the calculator for that, because you see the numbers are not so good. And the value will be negative 4.560328184. So it doesn't matter. So we can just calculate negative 4.56. So that's the value we found. But I can tell you that the actual minimum value will be negative 4.57142857, etc. So as you see, the optimal value is not so far from our second iteration. Even though we didn't start with a good number, we reached very good approximation of our answer even in 2 iterations. So if you continue that, you should adjust the eta value because it's too large of the learning rate. I used large learning rate here just to jump to a better value, but then you need to adjust eta to decrease the speed at which we learn, and you will get to the optimal value. So that's all what I wanted to show you.